In our last lecture, we introduced alkenes as a class of compound that possessed a carbon-carbon double bond. And we said that a key feature to this carbon-carbon double bond was the nature of that second bond. Okay, we said that one of the bonds was going to be a sigma bond, whereas the other was a much weaker pi bond. And that pi bond was actually outside of the axis between the two atoms, or the two carbon atoms of the double bond. So really what this thing looks like is kind of like this, where we have the two carbon atoms being held together by overlapping sp2 hybridized orbitals. Okay, and then we have the p orbitals on each one of these carbons overlapping with one another. And when they do, they create a molecular orbital that kind of looks like this big cloud over top and over bottom, or under bottom, you get the idea, where we have an area where the electrons are going to be hanging out. Okay, and it's this area right here, this region of the molecule, that is electron rich. Okay, and because it's electron rich, that means it has a high propensity of going after things that are positively charged. Okay, so if I had an alkene, I'm just going to keep on using this kind of general structure for an alkene here where we're not worried about the various substituents on there. Okay, and we were to expose this to something that's positively charged, like a proton. Okay, the electrons that are in that double bond will attack that proton. Now you have to remember, there are two electrons that are in this double bond. Okay, and they're being shared across these two carbon atoms. Okay, so that means that if these two electrons are used to form a bond with hydrogen, okay, that means that one of the carbons is going to wind up bound to the hydrogen, okay, where we have both of those electrons being used to form that bond. Okay, and the other carbon is going to have nothing. Okay, it's going to form a carbocation intermediate. Now, of course, at this point, anything that has a negative charge or a pair of electrons, which we'll call it a nucleophile right now, will come in and then attack the positive charge that has just been formed. Okay, so the overall effect is the formation of these two sigma bonds and the breaking of the pi bond. Alright, so now if we look at this slightly differently, instead of looking at it as the alkene being reacted with something that is truly positively charged like a proton, which we know is not a typical situation because ions don't usually just exist by themselves. What if instead of that we had that alkene reacting with a molecule that had a part that was a little bit positively charged and a part that is a little bit negatively charged? Okay, because if we had that arrangement, then the electrons from the pi bond would attack the more positive side of the molecule, and that would break the bond between the positive side and the negative side there. So what we would wind up with is initially getting a bond between one of the carbons and A, and like we saw before, we would form a carbocation rearrangement. I'm sorry, getting ahead of myself there. We would form a carbocation intermediate, which we said could rearrange, but let's not worry about that right now. Okay, and then of course we'd be left with some anion. Okay, and then that anion could come in with its electrons. We don't know how many are there because we haven't identified it yet. And that will form a bond. And get us to a product. So again, you can imagine anytime we have a scenario where we have these two parts of a molecule, one that's kind of positive and one part that's kind of negative, we can make this work. And there's a ton of different ways that we can do this. We could do this with hydrogen halides, so like HBr, HCl, or HI. We can do this with water. Okay, again, it kind of fits the same motif here. And we're going to see that there's a whole bunch of other things that we could do. We could do halogens. Oops, let me draw that a little bit more generally. Now you're probably looking at this and thinking, well, how could you possibly do this with a halogen? They're the two of the same element. They don't have a positive side and a negative side. Well, we'll get to that a little bit later on. Okay? And there's also a way for us to do this where we use a combination of a halogen and water. And what we wind up doing is using the X to add to one side and then the hydroxy group to add to the other side. But again, that's something that we're going to talk about as we kind of go through these reactions. Alright, so let's focus in specifically on one of the types of reactions that I just mentioned. And that's what we call a hydrohalogenation reaction. Okay, and you can see in there the words, or at least parts of words, hydro and halogen. So this is a reaction that is going to add a molecule that contains an H and some halogen across the double bond. Okay, so a generalized form of that would look like this. Okay, and as the reaction proceeds, we wind up breaking the pi bond, creating a carbon-hydrogen bond, and ultimately creating a carbon-halogen bond. Okay, and I know I mentioned this in class, but we have to be careful here because I know that fluorine counts as one of the halogens, but its reactivity is a little bit different from the other ones there. So this really pertains to chlorine, bromine, and iodine. Okay, and the mechanism for this reaction is just like what we've just been looking at. Okay, so in the mechanism for this reaction, we start off with the electron-rich alkene coming into contact with the hydrogen halide. Okay, remembering that the pi bond is electron-rich, so it's going to be seeking out things that have partial or full positive charge, which makes that H there look pretty darn attractive to the electrons in the double bond. Okay, we know that H hydrogen is going to be monovalent, so this bond has to break. Okay, when that does, just like we saw before, the two electrons that make up the pi bond are going to be shared between one of the carbons and the hydrogen. Now, in this particular case, it doesn't matter which carbon because, well, I haven't defined what's on or what's attached to each one of the carbons. Okay, and again, we wind up with this carbocation intermediate. And anytime we have a carbocation intermediate, remember we have to be on the lookout for rearrangements. But I'm not going to do any of those quite yet. All right, so we have our carbocation, and then, of course, the resulting halide, which has no problem attacking the positively charged carbon now. And then we wind up with our product. Okay, which is an alkyl halide. Okay, so now for a more specific example. Okay, so let's say we start off with cyclohexene. Okay, where we have this double bond on the six-membered ring. Okay, and we are going to react that with, say, HBr. Okay, so the product that we're going to form here will involve the breaking of the pi bond. So remember, the pi bond was between these two carbons here. If you want, you can actually number the carbons. Some people like to do that to kind of keep track of things. Now, I'm not worried about which order I go around because I'm just numbering them to keep track of them. So 1, 2, 3, 4, 5, and 6. So I know I'm going to break the double bond between carbon 1 and carbon 6 here. Okay, and I know that I'm going to form a bond between carbon 1 and the hydrogen and carbon 6 and the bromine. Okay, and that's our answer. Okay, now this particular example that I've shown you here, it didn't matter which carbon got the hydrogen and which carbon got the bromine, but sometimes it does matter. Okay, where it matters is when we have an alkene that is not symmetric. So we don't have the same thing on both sides. Okay, so let's say we have an alkene where one of the carbon bears two hydrogens and the other carbon has two methyl groups. Okay, and the question is, what happens if I try to do a hydrohalogenation with this? Okay, there are two possible outcomes that we could imagine. Okay, either when we get the attack taking place on the hydrogen's going to go to the carbon on the left or the carbon on the right. Okay, now if it goes to the carbon on the left, this is the product we're going to get. Okay, and if it goes to the carbon on the right, this is the product we form. Okay, so you can see that in the product on the left, okay, the H has gone to the carbon that is more substituted. In the product on the right, the H has gone to the carbon that was less substituted, the one that has more hydrogens. Okay, and it turns out that the only product that forms is the one on the right. Okay, we don't get any of the product on the left. Okay, so we need to be able to justify this. Now, we know that the first step of this mechanism is going to involve having the double bond attack the HCl. Okay, so that would look like this. Okay, and when that happens, we're going to wind up forming a bond between one of the carbons and hydrogen. The other carbon is going to be left with a positive charge. Okay, it'll be a carbocation. Okay, now if the H goes to the goes to the carbon on the left-hand side. Okay, this is the intermediate that we form. Okay, this is our carbocation. The other possibility would be if the hydrogen went to the carbon on the right-hand side. If that happened, the carbon on the left gets the positive charge, and we generate this carbocation intermediate. Okay, they're both carbocations. Okay, they're both, well, they're both unstable relative to the starting materials or the products, but by comparison, the one that's on the left-hand side is a primary carbocation. Whereas the one on the right is a tertiary carbocation. Okay, and we know that that's going to be more stable. Okay, at least relative to the primary carbocation. In fact, anytime you see somebody write a mechanism that involves a primary carbocation, you should start questioning what they know about what they're doing. Now I'm going to have to be careful when I write my mechanisms in front of you folks. Okay, so you can see that the first intermediate that I drew, okay, when chlorine comes in and attacks, okay, will lead to the product on the left-hand side. Okay, and when it comes in and attacks on the intermediate on the right, we have formation of the product on the right. Okay, so when you think about it, okay, we can kind of explain this through an energy diagram. Okay, this is going to look a little bit different from the reaction diagrams that I've drawn in the past. Okay, so instead of starting all the way on the left-hand side, I'm going to start in the middle. Okay, and this is going to be our reactants. Okay, so this is our alkene and our HCl. Okay, now, if we look at the products on the left-hand side, we go through that primary carbocation. So we'll call this the primary carbocation. Okay, relative to the tertiary carbocation, which I'm going to draw on the other side. Okay, the amount of energy required to follow the path on the left-hand side is much greater than for the right-hand side. Okay, in fact, we can look at the activation energies for each one of these. Okay, we can see that getting to the tertiary carbocation is going to be a lot faster because it has a lower activation energy. So lower activation energy means faster reaction. Okay, so That's why the reaction that forms the right product, or I should say the mechanism that forms the right product, results in the only product that's going to be formed. Okay. Now there's one other thing that we need to look at with hydrohalogenation, and that is stereochemistry. Okay. And to explain stereochemistry, it's helpful to look at a cyclic system. Okay, now let's start off with 1,2-dimethylcyclopentene. Okay. Well, actually, let's write it the way that we've been writing it this whole time. Okay, the reaction of this alkene with HCl, okay, is going to produce a hydrohalogenation reaction. Now here again, we're not worried about which carbon gets which part of the molecule because it's a symmetric molecule. Okay, so we're going to form this product here. Oh, whoops, not that product. This product. Okay, now the question is, what are the stereo or relative stereochemistry is going to be for these two carbon or these two stereocenters right here and right here. Okay, and there's a whole bunch of different possibilities. Okay, so we could have both methyl groups coming forward and a chloride going backward. Okay, and we can have the CH3 coming out towards us with the H going backward. Okay, or we could have had the enantiomer of that. Where we switch both stereocenters. Okay, and you can see here that there's one other possible, actually, there's more possibilities than that. There's two more possibilities that involve having the methyl groups on opposite sides of the ring. Okay, that's one possibility, and then here's the other. Okay, and frankly, chances are we're going to see a mixture of all of these. Now, the reason why we see the mixture is because in this reaction, we're always going to be forming a carbocation intermediate. So remember, carbocation intermediates are going to be planar, okay, completely flat. So attack from the top face is just as likely as the attack from the bottom face. Okay, so we would expect to have mixtures of products. Now, there are going to be some cases where we don't have a whole bunch of diastereomers forming, but rather just two possible enantiomers. Okay, so let's say we have, actually let's make it a six-membered ring. Okay, and what we're going to do here is we're going to put a pair of methyl groups on this carbon, and we'll put one over here on this carbon, and we'll put a double bond between the two. Okay, so then, and I'm going to put a line here so we don't confuse these two problems. Now, if I were to do a hydrohalogenation on this, again, we'll use HCl. And you can see I've just written the reagent over top of the arrow there. It's the same as if I had put a plus sign and then written the structure of the reagent. Okay, and there's two possible products. Okay, either we can have the chlorine wind up going back away from us, okay, or we could have it coming out towards us. Okay, and as you can see here, these two are enantiomers. The reason why I just kind of drew the H without stereochemistry is because in both cases we're going to have two H's. One that was already there and one that we put on the molecule. So I'm not worried about that stereochemistry. So again, these are enantiomers, and they arise from the fact that the first step of this reaction mechanism produces a carbocation. Okay, so we said it's going to be planar, and that plane is going to bear all three of the carbons that I'm highlighting here, including the one that bears the positive charge of the carbocation. Okay, so here we can get attack either from the top face, okay, or from the bottom face. Okay, and depending upon which side it attacks, okay, that's going to determine which enantiomer is formed. But there's, again, no reason to think that top side attack should be any more or less favorable than bottom side attack, which means that we would expect a 50-50 mixture, and therefore a racemate, or a racemic mixture. Okay? Alright, so that covers hydrohalogenation. Now the next thing we're going to turn our attention towards is hydration reactions, which are very similar in a lot of ways, but there are a couple of unique differences that we need to cover.